Okay, ladies and gentlemen, welcome back to another week of EECS 498 Game Engine Architecture. It's good to see you. I hope you had a relaxing weekend. I know that some of you did not because the Homework 8 submissions were coming in very fast. But one thing that was really encouraging was last year we had one student finish Homework 8. And this year, we have tons. A lot of you have done a great job on Homework 8. And things have gotten easier in this course since last year, but it's still not easy. And it's very easy to forget about that, okay? That what you're doing is so hard that sometimes when I tell other lecturer colleagues, they can't believe this course even exists because students, undergrads, can't build a fully featured engine in 3-4 months. That's just not really a thing. And so what you're doing is very impressive. Even if you're behind, just keep that in mind, okay? You're on homework 6 or homework 7, you still got a chance. You're still in it, okay? And keep in mind, right, lots of points at the end of the course, not too hard to get. The exam's going to be fairly friendly. Even if you're behind, you put in a good effort on that engine, try and finish it up. And you could come out with a much better grade than you're expecting, okay? Even if it looks a little bit dire right now. Okay, I'm not sure why my canvas is rendering like this. You're seeing this, right? No one else has this problem, just me. And I'm not exactly sure what's causing it, but today all of my schedules have kind of broken. But if you look at where we are through this really thin little lens, we are finishing up Homework 8. Okay, we have one final auto-graded Homework 9 assignment. It is called Data-Oriented Design, and that's going to be our main focus of the day, okay? I'm going to tell you more about this homework. It is very fresh in my mind, so I don't think it's going to take a ton of your time, all right? I don't think it's going to be the world's hardest homework, but then again, sometimes I get that wrong. So hopefully it'll be okay. You're going to have 1 week to get that done, actually slightly more, because if you didn't hear, Homework 8 was extended 24 hours last night. The reason it was extended is because I had to basically take control of all the autograders to get Homework 9 loaded on and tested. Thus, no one could submit last night, which was prime time for finishing up Homework 8. So you got 24 extra hours. Now, that backs you up on Homework 9, so now Homework 9 has to be extended. So we extended Homework 9 48 hours. And so it's going to be due basically midway through our exam prep week. So you'll still have a couple days without any of these homeworks to think about, to just focus on the exam. And if you finish Homework 9 early, you get to focus on the exam earlier. I will say that there's probably no better studying you can do for the exam than working on these homeworks and getting these things done. And so try and do the best you can to get these homeworks done. Think back on your previous homeworks, the technologies you used, the techniques we discussed in lecture. You're going to want to go through Game Engine of the Day again, and we'll get to all that stuff during this exam week that's coming up, okay? Next week. This week, it's about data-oriented design, so that's what we're going to talk about. And then after the exam, you're kind of home free, okay? Grading gets a lot easier, and you got a lot more freedom, and you can focus on your other courses a little bit more and have some fun with your newly minted game engine, which you finally get to customize. I hope you enjoy doing so. Quick game engine to talk about for Game Engine of the Day. This is Adventure Game Studio. And screenshots, not super great, but you can kind of zoom in here and you can kind of see some interesting things. You're never going to believe this, but the UI here has basically a hierarchy view of all of the different interactable objects and stuff you have in the scene. When you click on one, you get a smaller, more detailed view, an inspector view, kind of showing you what properties that object has. You have a viewport or a scene view to kind of show you all of the things, how it's laid out in the scene, how the artwork looks. One really cool thing is that there are actually these toggleable overlays that allow you to see where characters are allowed to move and where they're not in the 2D artwork. So this 2D artwork is just a 2D grid of pixels, right? So the engine doesn't inherently know that this is supposed to be the floor, the z-axis. So you have to draw that in, and you can do it. I don't know of a ton of popular games that was made in this engine, but it has been around for a long time. It's a 1997 engine, and yeah, hopefully you can hear me a bit better now. It's a 1990s 97 engine. It was created by Chris Jones, and if I would say it's famous for any game, it would be the 7 Days a Stranger series of adventure games. Anyone play those games? Well, yeah, probably not. A little bit obscure. Has anyone ever heard of a online YouTube series called Zero Punctuation? Okay. Made by a person named Ben Yahtzee Crawshaw. And before he got really popular with his video series, you can kind of tell he's a strong writer because he made this series, okay, 7 Days a Stranger. Those are his games. They're very good. Very witty adventure games, and they have some action in them, if you can believe it. This is not just walking around and putting the right puzzle item on the right place and saying the right thing to the right person. No, like, these games tend to devolve, and I say devolve, I should say evolve. They tend to evolve over their runtime into, like, there's a serial killer in this area. I have no idea what door they're going to pop out. I have to solve the puzzle before they get me. Right, so very cool, especially if you're into survival horror, which apparently Yahtzee is as well. There's a website for it. It was made in the UK, it seems, and yeah, lots of cool stuff, sprites, animations, and stuff like that, cool images and all that. There's scripting support. They seem to use a language that is similar to C, though its syntax actually reminds me more of JavaScript than C. And apparently there are thousands of games, but what matters are the number of good games, and not so much just quantity. A warning, I think last year I went to download it, and my antivirus was getting spooked by some stuff in there. So yeah, be careful if you download it. Some engine tidbits. Yeah, developers draw the walkable areas to help the engine understand in a piece of 2D art representing a background, right? Where can I walk, right? What occludes what? You can create characters. You can create inventory items. It has a database system kind of similar to that of RPG Maker. And the scripting language, right? It's based on C. So if you are bored, right, 5 Days a Stranger, I think 7 Days a Skeptic. Why say 7 Days a Stranger? It's 5. Here we go. And yeah, it's really good stuff. Okay, so any questions or comments on Adventure Game Studio? Anyone ever hear of it? I'll tell you. Okay. There are these game engines that dominate the market, okay? Unity, Unreal, how do we compete at all? Okay, this is how you compete, all right? Unity is great for just about everything, but it's not excellent at making adventure games, especially in that old classic style. But this engine absolutely is, okay? So you want to make a game engine that can fight today? Aim it at a niche, okay? Specialize that engine so that people will say, I could use Unity or Unreal for this, but this engine, your engine, is exactly perfect for the topic, okay? And that is how I recommend you go about doing it if you actually want to fight with your game engine and see if you can grab any amount of market share, okay? All right, let's keep going, okay? Yeah, I think, most of you know I kind of got whacked by the autograder last night. This is me at 3 a.m., and I think if you look really closely on there, maybe you see the 3 a.m. or something. But in the Beister Building office, and the autograders are right here. You can see the Mac. Which one is this one? You can see Mac OS X2 is right here. And the problem is that I took this photo, and then I had another 90 minutes of solving issues. So I actually left about 4:30 a.m. That stunk. Yeah, but anyway, yeah, I had to upgrade. I couldn't go home until I upgrade the lives counter for this assignment, right? Like you just can't do that. So I had to stick around. So anyway, yeah, my apologies if my vocals and vocab are a little bit off today. Okay, final all-graded assignment launches today. You'll be the first ever to experience a homework 9. Last year was just a 50 free points, okay? So you have to wonder if they would consider themselves lucky because they got a 50 free points, or because they missed, or not so lucky because they missed the cool assignment. Hopefully it'll be cool. Anyway, so expect some rough edges on this homework 9. The level of polish, I think some of you said with homework 8 isn't quite the same as homework 7. That's because homework 8 was rushed last year, and this time homework 9 is rushed. Okay, but it seems to be in good shape as far as I can tell. Homework 9 is very difficult for the auto graders to handle, so it was difficult to submit homework 8 last night. As a result, we extended homework 8 by 24 hours and homework 9 by 48. We'll be watching homework 9 closely, given its newness and likely existence of assignment spec ambiguities. We did consider extending it to Wednesday of last week. Yeah, so this should say, let us know if and when you run into problems, so we can polish it up. There's this a bugaboo in the games industry where a developer who didn't put a ton of time into Q&A will just kind of poop their game out into early access on Steam. Thus, you have a bunch of paying, not customers, but paying Q&A agents reporting issues and helping you fix bugs and fix balancing issues. It is pretty regretful when a company basically outsources their Q&A, because the initial people pay money, or you're punishing your early adopters. Sometimes, though, logistically, it's like there's just not really a good way to get around that, especially if you're making a massive multiplayer online game. It's like, what else are you going to do? You try your best with your small team, but you only have so many friends and families you can coax into playing the game with you. And maybe if you run out of money, that's just the end of the story. You just got to do what you got to do. But in any case, one really tough thing for me is that it's been 10 years since I was in your position. And I kind of still have that mentality, and I kind of can predict what'll be hard and what won't be hard, but it's getting harder every year. Okay? So sometimes I'm surprised at the fun bugs and errors and ways to lose time that students discover on these homeworks. And so please let me know when you found a new one, and I'll punch it into the autograder or fix the spec or something. Just yesterday, I can't remember who, but someone recommended a new test case. And I'm like, yeah, that's a great idea. And so we'll add that, and over time the course gets better, but it's just very hard to predict that stuff. Anyway, okay, so we should talk about homework 9. Let's do it, all right? I've been itching all day and all yesterday to do so. So homework 9, we are moving from the world of object-oriented programming to the world of data-oriented programming. Speed is what we need, and object-oriented programming, as we're going to talk about soon, just isn't really capable of getting us that, okay? We are moving into a world where the experiences we make can feel a lot more juicy, a lot more real. If you look at this scene right here, one issue is that, like, in the real world, in most environments in the real world, like, there are little specks, dust floating in the air, leaves, okay, coming from the trees, right? Rain, little drizzle drops of rain, okay? The real world is so very rarely static. The real world often has a ton of motion to it. And we really just kind of struggle to make that happen in homework 8, okay? Yeah, we can create actors, but you create too many and you're going to quickly start to slow down. We really want a way to iterate very fast on artistic, beautiful, like, multi-particle effects, okay? We want millions of cool little icons and images and things floating through the air with different physics and different motion colors that interpolate as the lifespan of the particle goes on. We want to not only create streams of particles and be able to aim them and change their shape, but we also want to be able to do bursts. We want to be able to do bursts in response to Lua calls. So for instance, in the Donna Shmup game, when an enemy takes damage, we would like to send some sparks flying, right? To better sell the pain that we've inflicted on the salty boys. What about things like this? If you want to create kind of magical or mysterious entities, I really like this image right here, this tiny GIF. It kind of looks like a fiery bird, like an almost magical bird flying through the sky, the kind that could turn into a really cool like boss fight or something, right? And all that stuff has got to be really easy. I want to be able to do that in seconds, not have to go in and program a bunch of stuff in Lua, and then it runs too slowly, so I can only have one Firebird, and I wanted 100 Firebirds. Thank you. Okay. Things like fog over here and smoke, which you can see in the assignment spec. Okay. All these gorgeous effects help make a game feel polished and professional, and we just don't have the capability to do that when you finish homework 8. But we do when you finish homework 9. Okay? And so these kind of beautiful effects, right? This doesn't look like a test case from this course. It looks too cool. Okay? And imagine that there's not just the black background. Imagine like, yeah, it's the Donna game, but now she's flying through like a snowstorm, and it's cool, and you got enemies that are like snow enemies now. And it would just look fantastic, right? And you could make the particles go even faster over time to indicate speeding up of the flight, right? Bursts, we already talked about that. Super good for gameplay mechanics, right? When Mario jumps in a modern Mario game, what do you do to sell that? Well, you burst a little cloud of smoke right underneath his jumping location, and it looks like he pushed hard and kicked up some dust, right? All those little things. We want to be able to do that. You want to create a game about firefighting or anything with fire in it, then this is how you're going to do it, okay? Particle systems. This actually kind of looks like almost like someone threw down like a rescue smoke signal. Is that what it's called? You're on like a deserted island, so you throw these down, and now someone flying by sees it and radios you in. Yeah. Jose, you had a question? Yeah. But pretty cool stuff. There are a lot of particles going on here, okay? I think this is like 50K particles, okay? Now, the performance test cases you're going to have, one of them, well, I had to change them because the Linux autograder is just too slow to handle it. But last night we had a 1 million particle test case as the final test case. Yeah, Mac Mini could handle it. Linux EC2 instances, no way. No, they stink. I have to pay for the super expensive GPU instance if I want to do that. It's like $1 an hour. Yeah, we don't have budget for that. We don't have a budget for much of anything. Okay, yep, cool, beautiful effects. It is surprising how beautiful of an effect you can get with just a bunch of squares that change their shape and tint over time. Not a very complex effect, okay? The kind of things you have to implement in this particle system you're going to be making, not that crazy, okay? It's a small subset of what you can get done with Unity, right? Yes, question.
So how dramatic is the difference, like object-oriented versus data-oriented? Like, would the previous slide even run if it was object? I'm
going to guess the answer is no. And I have to guess because I ran out of time to do tests. But I'm going to be experimenting this week to be able to give you a better answer. I do have an experiment I'm going to do with you in just a moment to show you what kind of performance improvement you can get. Basically just doing the same thing but doing it much smarter. But in any case, this is going to be a really fun, I think for many of us it'll be kind of a fun homework because you'll get correctness, I think, relatively quick, and then you'll get to have fun experimenting with performance improvements, and you'll get to, experiment locally and then throw it against the autograder, see if you improve things. I think a lot of people really like that iterative style of development, right? It's very satisfying, just kind of chipping it down. Anyway, all right, this is the progress thus far. We started with that hard-coded text adventure game, not an engine, just a game. Made it modded. we added a basic, the gameplay was the same, that grid-based adventure-style gameplay, but we made it into a 2D engine. We then moved to the world of continuous collisions and continuous positions, right? We then made it all scriptable in the epic Homework 7 marathon assignment. Last week, we added physics, okay, box 2D stuff, so now everything feels alive and dynamic. And this week, we ran out of space, so look at this. Look at that. We just moved, and this week, you're going to be doing your data-oriented engine. And, it's all coming together, right? The only thing we're really missing is that integrated editor. Yes?
Is the physics-oriented 2D engine like a test case that exists somewhere?
No. It's that'd be pretty cool. You could probably recreate it, but this is the Box 2D physics testbed. And I remember last year when I got it finally working on a Mac, and I was like, I can't believe it. I just watched it for 5 minutes, enjoying the moment. Okay, particle systems, what are they? If you want to create special effects, right, there are a bunch of different things you can play around with. All of them tend to be difficult to deal with, all right, for students. One good example is shaders. How many of you have ever programmed a shader before? Okay, I'm guessing a few of you did, maybe in 494. We programmed one together in 494. But another big thing is particles, okay? You can, if you can render a lot of very tiny things very fast, then you can create a lot of very interesting effects. In particular, whenever I look at cool particle effects and systems, I always get the sense that fluids have entered the conversation, right? And the way that things flow here is not rigid like most of our actors tend to be. It is fluid and morphing and flowing and slushy and beautiful and radiant, right? And so with Unity, right, you can use their 3D particle systems to get really gorgeous effects like this, okay? Those people have a lot more time than we do to make their particle system. They get paid a lot more than we do to make the particle system, and so we're not going to be able to make something this cool. But we'll make something plenty cool, okay? I think you're going to like it. And you can always upgrade it later. Unreal Engine has their own particle system. It's called Niagara. And apparently it has very nice facilities for flowing fluids, okay? I think that looks beautiful. I'm not sure why our fluid is turning from like molten red to like teal. I'm not sure what's happening here. But yeah. It could be like a heat map that shows you how fast everything's moving, but I don't think that's right either, because things are moving very fast over here. But in any case, most game engines you use and pull off the shelf today will have a deluxe particle system package available to help you create beautiful effects like this. So our game engine should have that too, and it will. Uh-oh, I can tell I just made this a moment ago. Okay, hold on. Okay, cool. And then you got to go up here, got to paste these in. This is like when you violate the dry principle, but you violated it in slideshow, right? Now you want to make one change, and you have to update 10,000 different locations, okay? All right. Anyway, particles in smaller engines look good. Yeah, it works good. I want to show you a famous clip. This is a team that made a Flash game engine for a Flash version of Breakout, and they talk a little bit about particles here. It's going to be nostalgia for some of you.
There's this saying, like you can't ever have too many particles in your game, and it's, again, you can't make broad sweeping statements, but it's 100% true. Let's add some particles. We're going to start with the classic smoke. The ball hits something, we put a little puff of smoke in there. And you can use whatever particle engine you can find. It's kind of a trap for programmers, these particle engines, because you get stuck making one and you're making it the very best one and then you never use it. But it was fun making, so don't do that. Just find something that's already made, use it. You get
do it, it's like the simplest thing you can program. It's so much fun.
Don't listen to him. Don't listen to him. So we got smoke in the game, like smoke coming off the wall. We can do better. We can do better. We want to make something with the blocks. So we want to make the user disappear.
Okay, right. So you can see the smoke, right? There are a few other effects you can check out if you want to. But basically, right, even a tiny little engine for a demonstration purpose like that will go through the effort to create a particle system. Ghost of Tsushima is a game that came up earlier in the course, Sucker Punch. We've got a number of Wolverines there. And one of the reasons that Sucker Punch, despite being a relatively small AAA team, one of the reasons they make their own engine from scratch is because, and they've always had this, they tend to have the best particles in the business. And I'm also talking on PC as well. Okay? Of course, they are not allowed to go onto PC. Not really. I think, actually, did it get a PC port?
Yeah.
Okay. Recently, they've been allowed out of the PlayStation mines. But they are responsible for having the world's best particle system on a very cheap piece of hardware. Okay, so how do you make that work? Well, you have to orient your engine around that fact and making that work. Okay, so it's worth it to them for them to make their own engine and focus so heavily on creating a beautiful particle system that's also extremely fast and can run on a potato. Okay. And so, extraordinarily impressive work. And look at all this. Like, these leaves have shadows even. It is really amazing. One interesting thing here is that you see all the leaves. There are very few leaves that are far away from the camera. And that's kind of a hint that this particle system is working with constrained resources. They're beautiful. Oh, right here. It seems so thick. But if you actually look and try and find leaves that are like slightly further than the water's edge, you won't find very many, okay? Anyway, particle systems are kind of a gnarly thing, in part because they have so many different properties that you can alter on them, okay? Here is Unity's kind of default particle system. It's this cone shape. You'll be making something very similar, okay? You'll actually start with a circle shape, but then you will consider the circle a special case of an arc. Okay, where you define an angle, two angles, a minimum angle, a maximum angle, and you just emit between those two. I give you the math, don't worry about it. And you can change some things, right? So right off the bat, we got this particle system component, okay? This component is an absolute monster. Each of these little gray strips down here is something you can click, and it opens up an entire new category of things you can tweak and alter. In this case, we can move our particle system around. We can change its initial color. Okay, so that's kind of cool. But there are many other things you can change. Here are just a few that will be relevant to you when you make your particle system. Speed, so the initial speed at which you move. The initial size of your particle, right? So we can change the speed to go very fast or slow. We make the particles bigger, and we got this nice little smoke effect. That's kind of cool, kind of ominous, okay? But we can do many more things, okay? That emission, that continuous stream of emission, we can change that to be more of a burst. We can give our particles gravity so that they actually fall, all right, and they accelerate downward. We can change the shape, right? So it's not just this cone, but it's actually a sphere in all directions. Well, if you look, we actually are also linearly interpolating the size of the particles. They start at 0, and then they get much bigger. They also interpolate their colors. So they start as this really hot red, makes sense for an explosion, and then as their lifetime kind of progresses, they begin to fade out to a 0 alpha white color. So kind of like smoke dissipating into the wind, all right? And so all these things, actually everything I've shown here is what you're going to be making. And there are some other properties too, but not a ton more properties, okay? Yeah, this is hopefully going to be a shorter assignment for you. And I think you deserve a rest. You've been working very hard. Hope the burnout isn't becoming too severe yet. Anyway, the particle system component has just a massive amount of things that you can configure on it. And this is very common for particle systems. In Unity, you can just explore all of these for days. And you can do some extremely interesting and intricate effects by messing around with these. In your particle system, you won't have nearly this many. But you'll have plenty, okay? Plenty to keep you busy. It's a very common component in engines, the particle system. It is typically implemented kind of separately from the rest of the engine, in part because you really need a particle system to be fast, which means you probably want to use something called data-oriented design or data-oriented programming, which we'll talk about today. But when you're developing the rest of the engine, you probably want to be able to develop it faster. So you use object-oriented programming. Very nice, great for humans, not so great for speed, as you're going to learn in just a bit, all right? So anyway, particle systems are often kind of separate from the rest of the engine, and it's definitely going to be the case in your code base, okay? It's going to be a second C++ built-in component. This is not a component that your users have to write in Lua or that you write in Lua. No, you're going to write it in C++, but it really is just like how rigid body kind of was. That the fact that it was C++ is just very transparent to the user. Okay, you just don't care that much. Well, same thing here. In fact, one of my big tips for you is going to be to reuse your approach that allowed you to introduce the rigid body C++ component and just do those same things, and you've got a particle system component working now with its own onStart, onUpdate, and onDestroy functions. And you can just use those functions at the right time and do the right thing, and boom, you're good. You're emitting a bunch of particles, okay? These are not all of the properties that you need, but this is the vast majority of them, okay? We got things like a starting scale, and you can provide a random range that you actually start in. So some particles small, some particles big. You've got the radius that you want to emit the particles in. And people are looking at this and they're just kind of like, I can't tell if this is like grimace or you're excited or what, okay? But it's not that bad, I promise you, and I'll explain why in just a bit. You can change the image that the particle uses. You can change the gravity scale in the X and Y direction. You've got starting colors, ending colors, you've got rotations, you've got sorting orders, you've got drag factors, angular drag, the angle of emission, the X and the Y position of the actual system. And this allows you to do some pretty cool stuff, okay? Like, you don't want to go too much less than this or you really start to be like, yeah, you can't do anything, right? No expressiveness, no creativity. One of your missions as a game engine designer is to wonder about what your game designer users might be able to do. You want to provide them the biggest box of cool tools as possible because you don't always know what cool thing they'll be able to do if you give them the right set of tools, okay? Sometimes you make a tool not quite knowing what it's for, and then something cool happens with it, and sometimes the designer walks up to you and says, hey, this is all great, but I could use this extra little thing. Won't you give it to me? And then you go make it for them, okay? So anyway, yeah, the relationship you have with game designers is pretty unique, right? Usually you just have that relationship with an end user who's not a programmer, but like, yeah, you could have one of your users come up to you and say, hey, I really need a function to help me like open a URL in the browser. And then you go make it, right? And that's awesome, right? You can talk about what parameters you want and what kind of features you might want in that function, and it feels good. If there's a bug, your user might be able to tell you about the bug or how to fix it even, right? Because they're a dev, probably. Some tips for this final assignment, okay? You are nearly finished, okay? This is the end sprint. Whenever I was in track and cross country, I would always be feeling like I was dead for basically 90% of the race. But as soon as I could see the end finish line, it was never hard for me to sprint like crazy because you can see the ending, right? That's why, for instance, all my friends are like, Austin, why on earth are you at the Beister building at 4:30 a.m.? It's because I can see the finish line. How can you not sprint when you see the finish line, right? The hardest situation is actually when you're doing something really laborious and nasty and there's no finish line in sight, right? It's like this might be a continuous thing that never ends, or you don't know when it's going to end. Courses are really nice in that they end after 4 months, guaranteed, okay? So, what's the price? I'm okay to lose the rest of my hair if it's only going to take a couple months. and then I'm free again. Anyway, do the best you can, okay? Start early. I've said that on every single homework, okay? But I understand that, if you're not caught up with homework 8, you can't start early. That's just how it is. Do the best you can, okay? That's what matters. And you do the best you can. I think all of you are passing this course, and plenty of you are going to be very happy with your grade, even if you don't quite get this finished. We'll see what happens. I think the discussion section told everyone that, like, yeah, we'll curve on the exam. It's like, I'm probably not going to curve the exam because the exam's going to be easy. The average grade's going to be high, but it won't be easy, but it will be fine. I will curve, though, if I have to. So know that. Anyway, on these later assignments, you're probably going to feel your code base's quality. The easier this assignment is to get set up, the higher quality your code base probably is, okay? In any case, on homework 9, what you're making should probably be pretty separate from the rest of your code base, actually. Right? You feel the quality of your code base as time goes on and as your code base grows. Like, every code base is fine and easy to manage when it's tiny. But as time goes on and new things keep getting added, right, your earlier decisions will start to manifest in more and more painful ways. And that's when you can actually judge your code quality, okay? All right, you want more talk about that, take 494. Autograder off date is in 2 weeks, okay? So you've got some time to catch up, but again, if you are too far behind, some of that time will dip into your exam study time, so that's not too fun. Exam is in 2 weeks, about 2 weeks as well. If I think a couple of you have the special circumstances from the Office of Accommodations, going to be starting the exam a little bit earlier in the day, and then when the main exam starts, we'll shift you into the same room as everyone else, and everyone will take the exam. The exam's going to be 4 hours. Not going to need that. Most people end up trying to use it anyway. It's going to be designed for about 2 to 2.5 hours for a very typical attempt at the exam. I highly recommend you reuse your built-in C++ integration from homework 8. That'll make things really, really easy, so you can get rolling real fast with this homework. I want you to start programming with data-oriented design in mind, but know that performance isn't really a huge concern until you get to that final test suite number 4, the 5th test suite. That's computer science for you. That will have a lot of very heavy performance test cases. Well, not a ton, okay? And that's where you can really exercise your performance chops. A quick note, I don't think I did that great of a job optimizing the staff solution. So this might be the semester where actually you get through it really easily with just a few optimizations, okay? But next year, those poor students next year are going to have a whole year to optimize and figure out how to make things go even faster. So, oh well. Okay, lots of experimentation is required when you tend to want to squeeze every ounce of performance out of something like this, okay? Some examples for you. Some hardware targets, some pieces of hardware, some computers that your code runs on will have a very small cache. Some of them will have a larger cache. Some will have a smaller L2 cache, but their L3 cache will be larger, okay? And the decisions you make might get you blown up, okay? Or they might save you. And you don't quite know until you've done some tests, all right? How much memory should you reserve in your arrays, in your vectors ahead of time? Some CPUs have a really good branch predictor, and then some CPUs have a crappy one. Sometimes branch predictors are really good at certain things, but then they're bad at other things. Okay, well, how do you fix that, right? Well, you experiment, and you run tests, and you figure out what your particular target platform is going to respond well to and what it won't respond well to. How many of you have ever had a problem where, it runs super fast on Linux, but OS X is complete tire fire, and Windows is kind of mediocre?
My Windows is so much worse than the
Yeah?
others.
Really? Linux is by far the weakest hardware.
Well, I mean, like, relative to
Yeah.
the
OS X is the best hardware, most modern hardware by a mile, most expensive too. Yeah.
For me, Windows is my weakest target.
Yeah.
Linux usually has no problems once it builds.
Yeah.
Mac has it's weird. It's
Yeah.
usually a lot tighter.
Interesting. Okay. Yeah, and students sometimes come up to me and ask, and I'm like, I have no idea, right? All of these operating systems and the processors and memory sticks that they use, the RAM they use, all have their own quirks. And so the answer is to profile and to experiment. And usually that has worked out for students, so it does take some time. Only 5 test suites in this particular homework. And several of these test suites have a lot of test cases. Like we got to J, we got to 2J, that deep into the alphabet for test suite number 2. But that sounds bad, but it's actually very not. Because just like in homework 7, once you knock down the first couple test cases in a suite, they start falling like dominoes faster than you can even pay attention. And so it sounds like a lot of test cases. It's not going to take that much time. You just knock them down like flies really quickly, okay? So yeah, you're going to have a lot of new features, but each feature you add is going to be pretty similar to a feature you just added. And so it'll just be a few lines of code for many of these test cases, actually. And so, does anyone have any questions? Any questions? So, yep, one big thing, like the Linux Autograder, I'm going to try and experiment with it as the week goes on. But Linux Autograder, to prepare, it's about an hour. And to do and submit a grade, that's about 20 minutes. Okay? So I'm going to say right now, you get submitting as early as you can, because there might be a log jam toward the end of this assignment, and it'd be a real shame if you got 100% on everything, and then you just couldn't get that final submit in at the end, and you get that minus 20% on the final submit, right, for Linux. Yeah.
Do not be the guy that submits at 11:50, hoping that the autograder mechanism is at 11:50. No,
Yeah.
that's not 11:50.
Yep.
That is a
Yep. Yeah, you submit at 11:50, you're toast. On Linux, you're toast. Mac, you got a chance, very small chance.
Windows, you're
Yeah.
also.
What's the Linux, or what's the autograder preparing again? What is that mean?
Well, yes. So the way that the autograder works, because they all have different hardware and they have different operating systems, I can't go in and say, oh, this test case, full credit is if it completes in 5 seconds, because I don't know. On Linux, 5 seconds might be incredibly fast, but on Mac OS X, on the Mac Minis with their M3 chips, might be super slow. And so instead of trying to pin this down, what we do is whenever changes are made to the assignment or the autograder code itself, we rerun basically a compilation step where all the test cases are run through the staff solution, and that generates a bunch of statistics on how fast things are. It has to run it 10 times. Then we take the median. And that takes a lot of time. It also generates the correct output, and that's kind of stored and hidden away so that we know whether the student solution coming in is finishing correctly and if it's finishing fast enough. And so, when you change the autograder code, that could change the stats. When you change the staff solution or the test cases, that changes the stats on those. So any change to the assignment requires another prep. And the first person to request a particular homework for that autograder will get the preparing step. If someone else did it before you, then you don't get the preparing step, and it's much faster. So that's how it works. Yeah. The low-hanging fruit is mostly picked. Yeah, there are a couple things I could do to speed it up, but not much. Anyone else? Questions? Homework 9? Someone said they had homework 9's test suite 0 complete before I even released the assignment spec. Can't remember who it was. Lie. Because the autograder is not capable of even issuing grades for homework 9 until 10 p.m. last night. And it was very spotty at that. Now it's available, though. So go for it. Okay, anyone else? That wasn't even a question someone asked. I just offered that as a tangent. Okay, well, what I would like to do is I would like to help you understand this kind of mystical thing I keep talking about. data-oriented programming, there's this notion that you're going to need it on homework 9. And I think that is the case, unless I really messed up my optimization, which I might have. Data-oriented programming is the only way you're going to end up getting 100% on this homework 9, okay? I think maybe you could get 70 to 80% with object-oriented programming, but you want to get this thing perfect, you got to have data-oriented programming. And there is pretty much no other feature of a game engine that's more fit for data-oriented design, okay? It fits like a glove, and you're going to want to use data-oriented design. It's just going to be a very natural way to express your particle logic, okay? I want to show you some code, okay? I want to show you some code here. Let's go into it. Here it is, okay? And I encourage you to try and look at this carefully if you can, or watch the recording if it's nearby, or scooch up if it's too far away. I'm not trying to make anyone nervous or anything. But I've got this code base right here. And this is not, this is not anything related to, homework 9. Like, this is not homework 9 code, but you can take some ideas from it. What we're going to do here is we're going to create a bunch of actors, and we're going to do some very basic collision detection on those actors, okay? Let's go into experiment 0 and just kind of look at what happens. This is going to be an experiment where we're going to have, how many actors? We're going to have 100,000 actors, okay? The size of an actor in this test, right? This particular actor is going to end up being 592 bytes, okay? Each actor has a bunch of stuff in it, right? And that makes sense. How many of your actors, at least during homework 5 and 6, right? You had a lot of stuff in here, right? You had like HP and position and rotation and collider stuff and trigger stuff and all that stuff, right? So we got a big actor object. Now, we're going to kind of randomly just kind of throw this actor onto the heap, okay? Right? That means we're using the new keyword, or you could use malloc or something like that. But when you use new, you are allocating space for that actor on the heap, and you're just kind of putting that actor anywhere on the heap, right? It could be scattered all around the heap. They're at different locations. They're very far away from each other, okay? And what we want to do is we want to take these 100,000 actors and we want to compare their locations to each other, okay? So we're going to do an initial allocation where we're going to create all of these actors, all right? We're going to go through in 100,000, we're going to create a new actor. We put it on the heap. You can see that right here. The pointer itself is going to be put into a vector so that we can keep track of all these actors. And then we're just going to kind of set their position, X and Y, nothing too big. Then what we're going to do is we're going to go through our actors in a kind of n squared style for loop, okay? Go through the actors one way, check all the other actors, okay? And we'll see if the X and Y positions are the same. If they are, the number of collisions goes up, okay? And that's it. We then just report, how many collisions we had and how much time did it take. So the important part here is that we got a bunch of actor objects. They're very big. These actors are chunky. They got a lot of stuff in them, okay? And these actors are also being put all over the heap, just anywhere, okay? And what I want to do is I want to kind of look at how fast we can do this. So let's go ahead and run this code. Okay? I'm going to press enter here, maybe. Is it running? Remember? There it is. Okay, so we had a ton of collisions. I'm not even going to say what that number is. I need like commas to help me out. Uh-oh. Right. Do that again. So it's going to run an experiment here. I think it is. And we're going to see what happens. I'll give you a hint. This is going to be pretty slow. Why is it going to be slow? Any ideas?
Cache misses.
Cache misses? Well, what do you mean?
Each object has, let's say it takes X amount of bytes to store, and we only want specific bytes for the positions.
Yeah.
You can only get so much data from your hard drive into the cache.
Okay.
You can only store so many objects.
Yeah.
So if you have to load in
Yeah.
thousands upon thousands of objects.
Yeah.
It's
Yeah.
logic.
You see, there are a couple problems with what we're doing. Okay, number one, our actors are so big, that would normally be okay, but the operation we're doing, we only care about their position. So we have to load these big actors in just to get the tiny little position right in the middle of the actor. No way, slow. So this took about 8 seconds, all right, 8 seconds. Now what I want to do is we're going to run a second experiment. This is going to be experiment 1, okay? This is going to be very similar to that first experiment, but something has changed, okay? Something has changed. The actors are still big and chunky, but this time we're not putting those actors at random locations on the heap. We are putting them on the heap, but we're actually using a technique called placement new, which allows you to specify where on the heap you want them. In other words, we're doing what the vector class does. We're putting objects on the heap, but we're putting them boop, 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 contiguously to each other, right next to each other in a nice clean row. Very nice, okay? So, blah, 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 and you can see that happening right here. We create an active buffer. This care buffer is a buffer that ends up on the heap. How big is that buffer? Well, it's the size of an actor times the number of actors we have. We can now use placement new to actually say where we want that to be. Where do we want to put our new actor, okay? And so we have put them all in a row. They're not scattered around our heap anymore, okay? Now, let's go ahead and actually run this experiment, okay? Boop, there we go. Experiment 1 running, yep, same actor size, different placement, okay? And we can see we're a little bit faster, all right? So previously, we did it in 8 seconds, and now we did it in about 7, okay? What is that? Like 1 over 8. It's like 13%. Not bad, okay. But we want something better than that, okay. We want something better than that. So here's what we're going to do. We're going to run another experiment, okay. Experiment 2, and this is going to have the same number of actors, but this time we're not going to use the entire big chunky actor, because here's what we've done. We have taken the position data out of the actor. And now we can just look at the position data for every actor without loading the whole actor, okay? We call this a position component. And if you look at what this actually is, yeah, just a little tiny baby class, okay, with an ID, with a float for X and a float for Y. That is it, okay? We have pretty much literally just plucked some of the members out of the actor, put them in their own tiny object, and now we're just going to load those, okay? So here we are. We've got our vector pointers to position component. This used to be actor, big chunky actor. By the way, what's the size of position component? Position component is not 592 bytes. It's not going to tell me, I guess. It'll tell me later, okay?
Plus 2 floats, so that's like what, 16 bytes?
Yeah, it's going to be like under 30 bytes, I'm pretty sure. In any case, we are creating that new small component. Notice we're just throwing it randomly on the heap. Okay, so just randomly on the heap, scattered everywhere. Okay, and then we're just doing the same operation, except this time we don't load the whole actor. Right? This actors array is actually just the actor positions. I should have renamed this, but anyway, let's see how fast this goes. Same exact operations, same exact data. We're just we have put the data in a more convenient format. Our thinking has become very data-oriented, okay? We're thinking a lot about our data and where it is and how big it is, okay? So let's go ahead and do this. Run experiment 2, please. So anyway, 12 bytes. Oh, and it's already done. Couldn't even finish the description of the experiment and it finished that fast. So 12 bytes instead of 592 bytes, all right? And we still have another optimization to do because we're just kind of throwing and chucking these things everywhere, all right? And so I want to, you had your hand up, Jose? Okay. I want to have these not randomly placed in memory. I want to put them near each other. okay? Because if my cache goes to check out and grab one of my little actors, my position components out of memory, and all the rest are nearby, it'll probably end up grabbing a bunch of other ones too. So it's already in memory, and we don't even have to go back to memory anymore. Okay, so let's go ahead and just take one final quick look at experiment 3. I don't even remember what the optimization is for experiment 4. We're going to find out. Okay, so we still have the tiny little nice 16 or 12 byte position component. Now we have contiguous component placement in memory. So we are using placement new, like I showed you. It got us a tiny 13% improvement. Now I wonder if it'll get us an improvement now that we're down and moving much faster. You can see placement new being used right here. Okay, we allocate a buffer that can hold all of our position components, and then we go through and actually put them in that buffer on the heap. Question?
Can you explain the actor buffer?
Yeah, right here. This actor buffer, whenever you see char star, it's very deceiving, okay? Whenever you see char star, you could be allocating a 1-byte character on the heap, but more often, you just want a chunk of memory. You're going to use it for something else. You're probably not going to use it for characters, okay? Characters are 1 byte. Is that always true? I think it's always true, like in the standard.
As far as I know,
Yeah, and so char is just a very convenient way to say, hey, I want to create a byte of an arbitrary number. I want to create a buffer of an arbitrary number of bytes in length. And so you can kind of see us doing that here. You see new char and then an array, okay? How big do we want this array? How many bytes do we want? Well, how many bytes is a position component? Because the position component is the type that we're going to be putting onto that array one after the next. So this is the number of bytes we need. We got this many actors we want to do comparisons on, this many position components, and so this is the number of bytes we need in size, okay? And so now that we have this buffer, we can use placement new, which is basically just new, where instead of just saying new and then the new thing you want, you say new location and thing you want, okay? So this is just an address that takes the beginning location of the actor buffer, you know, which actor are we currently dealing with, multiply it by the size of the position component, and that's the location of the buffer we want to allocate this thing in, okay? That's it. It's not too crazy. The syntax, like always in C++, kind of funky, but not too bad. Anyway, let's run it, okay? Experiment 3. Let's see what happens. I'm always a bit nervous about this because sometimes, like, you just flat out, that should have made things faster, but it didn't. Okay, like that's programming, you know? Anyway, hey, there we go. All right, hey, that's a much bigger improvement.
Is that 2525?
Yeah, it's 2535. So what percentage improvement is that?
It's like 25% increase.
25%.
Closer to 23.
So when we had bigger actor objects, we got a 13% increase. But when we made our objects much smaller and put them right next to each other, we got a 25% increase. How can we rationalize this? We can fit more of these into that cache, right? Yeah, our objects got smaller. By the way, making those objects smaller usually a good performance improvement. And we can fit more of them in the cache before our cache has to kind of go back to memory to fill itself back up again. Yeah.
So what happens if you try and cache only like primitive data types, like you try and get the lowest common denominator of size?
What do you mean?
Like if we're only, instead of caching like using data oriented with like
Yeah. Okay.
structs of actors, we have like
Yeah, I think I know what your question is. So let's say that you're representing some colors and you've chosen to use an integer for R, G, B, and A, okay? But you say, wait, each integer is 4 bytes, but in SDL, we only go 0 to 255. I can use a short, which is like, what, 1 byte, right? Yeah, it's 1 byte versus 4.
Yeah.
Or actually, no, I think short is 2 bytes. Yeah,
Even like
so
a
you'd use
short-
a uint 8,
Yeah, that's
right? And that's going to be an incredible performance improvement, right? You just made things super small. Everything's going to fit in cache. It's going to be fantastic. And it's slower by 25%. What? That actually happened to me when I was experimenting with the staff solution performance. You know why it's slower by 25%? I can't tell you for certain, but integer is such a common data type that processors have special instructions, and compilers will notice it and can accelerate that stuff
Oh, that's cheating.
in a way that uint8 is like, what's that? I can't accelerate that. Yeah, it would make sense that it would be faster, but sometimes this is why you have to experiment and profile, everyone. Like, you've got this great idea in your head. Oh, I'm going to make things so much faster. You implement it. You're so proud. I can't wait. Here it goes. You click the button. Slower. That's just how it goes. Sometimes, yeah.
So generally, when using this kind of like data-oriented,
Yep.
structure, should we try and get, with the exception of this integer thing, 'cause that's the computer's
Yes.
thing,
Like, I would always
the
say
smallest
smaller.
possible
Yeah.
data type
Yep.
imaginable, like to the point where
Yeah.
you're like, okay, I just want to keep it to primitives as much as humanly possible.
Yeah, if you can.
Yeah.
If you can, right, you want these objects to be as small as possible. Otherwise, we would just be using the actor data structure, right? By pulling only the information we need for the operation, by pulling it out of the actor and dealing with that, we've dramatically sped things up, okay? By several times. Anyway, that's 3, and we're all in for a treat because I don't even remember what 4 is. We can optimize this more? Okay, the number of position components is still big. We're still using actor position component, okay? Okay, I got you. Now we're not using placement new. We're using std vector, which basically does what we're doing, okay? So now we're just using vector down here. So we're not using any new. We just have a vector here, and we are just pushing it onto the back. I could probably use like in place. I'm not sure if it would speed me up, but and then that's it. Okay, so let's go ahead and run this final test. And so there we go. Experiment 4, and 12 bytes. It's in a vector. Okay, it was actually a bit slower. Yeah, I'm surprised. That looks like. So I ran this earlier, and vector was very slightly faster than our experiment 3. So I think this is kind of fluky, right? Realistically, there's a reason the autograder runs your code like 10 times to figure out how fast it is. That's part of why it takes so long to grade on homework 9 and all the other homeworks. But the takeaway, everyone, right? The takeaway is this. Data-oriented programming, its heart and soul is right here, okay? You want to think about where are my objects, how big are my objects, and do they need to be as big as they currently are? Okay? One question you might say is, well, if we're pulling this data out of our actor, how do we keep track of our actors? And that's another interesting question as well, okay? So let's go ahead and let's look at this little slideshow right here. This is one of my favorite illustrations of the entire concept, right? You look at one of these and it's like, oh, it's obvious why data-oriented programming gets you a performance improvement, okay? This is an image, right, of an object-oriented approach, okay, and a data-oriented approach. In this scenario, you have bird objects, quite a few of them, and in particular, you care about the position data of this bird. So there's vector 3 in there. Now, the bird has a bunch of other stuff in it, and in your normal object-oriented, like C# approach, okay, if you're writing Unity C# scripts, you're probably doing this, right? You wrote some code to manipulate the position data of the bird. But in order to access that position data, your cache has to load in the entire bird, which has the bird's health, and its stamina, and its hunger, and its name, and its type, and all of its friends, and interests, and all that good stuff, right? And all of that data is irrelevant to our actual operation. Because we just want to move the bird, and yet we have to load the entire object in to access that stuff. So that stinks. That stinks, all right? The mission behind data-oriented programming is to say, no, I want to deal with and change the birds, but I only want the position data of the birds. So let's pull the position data out in such a way that we can just get the bird's position data and not have to fill our cache with a bunch of other stuff that is not useful at the moment. Okay? So the cache utilization of data-oriented programming on the left is much better at least performance-wise, than what we see on the right, okay? And that allows you to get a lot of very cool, very high-scale, very performant things going on, right? This is just the kind of stuff you didn't used to see in games because the hardware just couldn't handle it, all right? Just get wrecked, okay? But this is ECS and data-oriented programming, I think, within Unity. Unity does allow you to program in a data-oriented fashion using something called DOTS. What is it called again? Data-oriented technology stack, I think? Yeah. Anyway, they don't advertise it very well. But this is a position-related calculation. It's a cache loading position data for all actors. These big gaps are basically where you have irrelevant data, like the attack, the HP, right? The hunger of the bird. Okay, we don't care about that stuff, all right? And so we are not going to use it, right? We're going to pluck it out. Which do you think will be faster? Right, you already know. Okay, in fact, we just did the experiment that basically was this. Okay, this was the experiment. So anyway, fast and slow. Okay. Here, we have 75 positions that can be loaded into this entire big cache, okay? This big block that represents our cache. Whereas over here, the same amount of space in our cache, we can only hold 16 positions now. So we have to go back into memory much more often on the right, okay? And memory is very slow. Have any of you ever stumbled across or had a reason to visit this particular link? I think this is a pretty famous link. It is Colin Scott's latency numbers every programmer should know. And I think it updates every year. So 2020, yeah. Can I change this to 2025? Anything change? No? No. I don't think they have data for that. In 2020, right, you have all these different caches, okay? And, okay. There we go. You have the L1 cache, which is kind of like the first line of defense for your processor, right? Your processor is dealing with a bunch of numbers and variables and addresses and data. It pulls it into the tiny but ultra-fast, very close by L1 cache, where it can very quickly get and deal with that stuff. But if L1 cache fails, then what do we have to do? Well, we have to go to the L2 cache. Now, if you want to use the L2 cache, and this is driving me crazy now, the L2 cache is like, it says 4 times slower than the L1 cache, okay? It is bigger, so you can put more things in it, but the L2 cache is cheaper and much slower to use, okay? If you miss on the L2 cache, and you have to go and get stuff from main memory, you've gone from 4 nanoseconds to 100, okay? That is 25 times more. That is brutal, an epic slowdown, all right? And so, right, when you have all this data that you can get into this cache, okay, then you don't have to keep going up the chain nearly as much. You can save a ton of time. But if you're jamming these gigantic objects into your cache, well, you're going to have to keep going back to main memory for everything. You can't really use L1 or L2 cache, or you can't use it very often, okay? If you happen to not have enough RAM, do you know what your computer will do? I think old operating systems will just crash. But these days, like operating system, you've run out of RAM, it can keep chugging in many cases. So what does it do?
Is that the page file?
Yeah. It uses something called the page file. Basically, the page file is on your hard disk. So you've just turned your RAM and said RAM doesn't have what I need. So I'm going to go and I'm going to use my hard disk, my SSD, okay, which is a disaster for you. 100 nanoseconds, we're going to go to disk. Where's disk? Where's disk? That's the network read sequentially from memory. Nope. From SSD, okay? We've changed units. It's gotten so bad, all right? We've gone from 100 nanoseconds, which already was awful for us, to 49,000, okay? Brutal. So that's an absolutely massive penalty. And I really like how they put in here, like, yes, hard disks are awful, but the worst thing you can do is hit a network, okay? Yeah, which is definitely true. Anyway, you can also shift this over time because apparently they have data. And if you look, Main, some of these things are getting much better and much worse. Let me see here. Main memory used to be terrible, but has actually gotten significantly better. What else do we have? Yeah, even L1 cache used to be very slow at the beginning. Branch mispredictions have gotten much faster to deal with. Okay. Anyway, again, the whole reason for showing you that stuff is that over here, we're going way up the cache hierarchy before we can get our stuff. And we're doing it much more often, too. Over here, we're kind of chilling as long as possible in that L1, L2 cache, okay? And never going to hard disk. So, yep, look at all that stuff. L1 cache reference, yep, blah, 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 blah. Main memory, cache miss, 100-time penalties, okay? That's very big, all right? Big problem, okay? So this stuff is really critical for high-performance code. And this graphic, by the way, comes from an Elizabeth Baumel talk. She's a Unity dev, I think it's like GDC 2019, okay, talking about data-oriented programming versus object-oriented programming. Now, a quick reminder, why do we all learn object-oriented programming? Data-oriented is just blowing it out of the water right now, right? Why would you ever choose that on the right?
It's more human people and they take it.
Yeah. Object-oriented programming for most people tends to be a much more natural way to think about programming and our data, right? You've got a piece of data, okay? It is a, what? It's a light. My piece of data is a light. And that light object is going to have the radiance, it's going to have the location, it's going to be all packed together so that I can find it, mess with it all at once, and understand it all at once. And it's going to have all the functions packed in with it too, okay? All right? It's just very natural. Data-oriented programming is about taking those things out and just kind of flinging them into the wind, kind of. All right? Not quite. It is not that disorganized. Yeah.
This might be a stupid question, but for like data-oriented programming, packaging all of the smaller packages of data within our classes into smaller classes, does adding more functions to like the overarching full class make it bigger in memory?
I don't think functions make something bigger in memory.
Yeah.
Yeah. So functions, I think, are usually statically defined, and then it gets called. There's one copy of that function, and then when you call that function on the object, what you're really doing is calling that static global function, passing in the self-reference for that object, and there you go. Otherwise, we would have another copy of the same function in every object, and it would be huge, right? So I'm pretty sure that's how it happens, but I might be wrong.
Does that mean there's no advantage to using a struct over a class then?
I think certain languages do different things with struct than classes. I think structs, like by default, for instance, in C#, I think structs are always passed by value, so they'll be copied and stuff like that. But yeah, structs versus class, I think that means different things in different languages.
Oh.
Yeah.
So, say for like my actors, I
Yeah.
only store their IDs in a list, and I make the actors elsewhere. Like for this data-oriented thing, like what you were showing earlier, how you stripped out all the stuff.
Yep.
How would you like get back
Keep
to
them
that
together?
actor class like efficiently?
That's a very good question. We'll talk about it in just a moment, okay? Yeah, so on the left here, we have data-oriented programming, and on the right, we have object-oriented programming, okay? Have any of you, yeah, you've all done object-oriented programming, right? This is more or less what that looks like, okay? Here you have a struct or a class, and it's called actor, and you've got HP, you've got attack, you've got defense. All these things that the actor has are kind of packed together in one object, okay? Pretty cool, super easy to reason about. There's a reason we all learn it this way. But as your actor grows, this becomes very chunky and it begins to waste a bunch of space in your cache. Okay? We've created right here what we call arrays of objects. Right? We've got an array here, and within that array are a bunch of objects. Okay? So scanning down that array, we're kind of forced to load in everything all at once, which isn't so great. This is a big problem if we only care about the attack. Maybe this is the battle system. And the battle system doesn't care where you're positioned or, other stuff. Well, it probably would care about those things, wouldn't it? Battle system is a bad example. But maybe we have some logic that only cares about the attack. Okay? If you've done data, have any of you done data-oriented programming? Yeah, okay, I know. you may have accidentally done data-oriented programming. If you programmed before you learned about classes or structs, there's a very good chance you did data-oriented programming without realizing it. Because if you do not have structs, if you do not have classes, data-oriented programming is pretty much the only way that you can recreate, and organize and deal with multiple actors at once. Okay? An example, I was doing my EECS 183 homework during an assignment, and classes and structs were banned because they weren't introduced yet. But the number of objects, the number of animals, let's say animals, with their HP, their speed, their location, was not finite. I couldn't just type and copy and paste them all in. So what do? What can you do in this situation? What is the technique I used?
Make a bunch of arrays that hold the individual component.
Boom.
pieces.
One array per property. And how do you identify an actor when you have a bunch of arrays, one array for each property?
By index.
By index, okay? If I have an array that has 5 HP values and an array that has 5 attack values, what is my actor 0? My first actor. It's the set of values that is at index 0 for all these arrays. It's a bit ridiculous, but that's how I had to do it. There's no other way to do it without structs and classes, at least that I could think. So here is the same situation, okay, from just a moment ago. Here's our object-oriented approach. And down here, we have our switch, our conversion to a data-oriented approach, okay? So here, right, we have not arrays full of objects, but we have an object with a bunch of arrays, okay? It's kind of a strange name. Basically, instead of arrays of objects, you've got arrays of properties, okay? And so, right, up here, right, you got your HP, your attack, your defense. I want you to tell me right now, tell me right this instant, how many actors exist in my game? 5. How did you know this? It's because our database over here of properties has 5 columns, okay? Each row is a property, each column identifies an actor, i.e. each index identifies an actor, okay? Where did the actors go? They're in the index, right? They're in the column, okay? What about performance? Well, here's the thing. If I only care about the attack, what can I do to improve the performance of this for loop? What can I do if I only want to print out the attacks? I only want to load the attacks into cache.
Just remove lines 14 and 16.
Boom. Boom. 14 and 16 are gone. I get rid of these lines. Now, right, that data exists, but in this for loop, I will never load the defense values into cache, and I will never load the HP values into cache. Why should I? They are irrelevant to me, okay? Before, I was forced to load those things into cache. Now, I have a lot more choice. I can still load them in if I want to do some math with them or they're important to the operation, but they're not, okay? So what you've really gained here is flexibility in how you traverse and load your data. That's why people tolerate C++, okay? The language that has a ton of footguns but allows you to mess with data at a pretty low level, okay? All right, so here we go. We've made the conversion, and this is going to be faster, okay? We've gone from having to pack defense and HP values in here and messing with our cache, and now it's just attack all day, okay, and nothing else. So it's really nice. Okay, so becoming data-oriented, right? Just by thinking about our data layout and the way that we access and use our data, we are becoming more data-oriented just by having those thoughts in our head, okay, and trying to make it right. So a question for you, and this is a classic question you will see on interviews. You see this everywhere. I saw this on an exam in 370. I got it wrong, okay? My dyslexia might cause me to get it wrong again. Okay, which of these two is faster? And if you struggle visualizing this in your head, you're not alone. I had to stare at this for like 30 seconds last night. Yeah, one of these is dramatically faster than the other.
I need to draw a grid for this.
Yeah, I had to draw a grid too. Yes, you're right. You are correct.
Yeah.
How do you figure?
The inner loop is accessing like the most inner array.
Yep.
But if you flip it, now you're grabbing the one element from this array, then you have to go to the next array to grab that one element.
Yes. Yeah. I kind of think of this as like you're becoming more granular with every index, and you really want to finish off everything in your J before you go to the next I. If you are constantly, swapping your I, well, you're going into I. You're going into the city of Ann Arbor, and you're going to get the burger. And then you're going to the city of Columbus, and you're getting the burger. And then you're going to Detroit and getting the burger. And then you decide you want pizza. So now you're going to city of Ann Arbor getting pizza, right? City of Detroit getting pizza. City of Columbus getting pizza, okay? Whereas over here, you deal with the more granular stuff, and then once you're done with everything granular, you go less granular and change that. So here, we're going to the city of Ann Arbor, we're getting the burger and the pizza. We're there, so it saves us a bunch of trips, right? Then we switch. We're done with that granular part. We go back to Columbus. We're going to the city of Columbus. We're getting burger and pizza. Good. Now we're going to Detroit, burger and pizza. One of these is way more efficient than the other. Far fewer trips, okay? And here's how you can visualize this in memory, okay? Look at these. Right here, if you ignore this right here, we have an array of items. We have an array, in fact, of arrays, like this, okay? Now, over here on the left, we're doing probably what you would think to do, okay? We're looking at our first kind of index, right? We're going to our first city, and then we're going to check out, right, the pizza, the burger, the wings, the sushi, all that good stuff, okay? When we go and grab this first item, our cache is going to end up loading all of this in, all right? And so we don't have to hit the cache a bunch of times. It's already there for us. One memory access, and then we got everything we need, okay? Super efficient, super nice. When we're done with this row, we're done with the city of Ann Arbor, we're going to Columbus, okay? And we're going to get to the burger, the pizza, the sushi there, okay, before we go into the next city, all right? And it's really good. Works well, right? So pretty good cache usage, okay? Over here, it's the worst cache usage you could design, okay? Right here, we are going to go to, let's see here, right? We're going to go over to this array 0, okay? But then we only want this item. We only want this first item right here, okay? And so our cache is going to load in all of this, but we only grab the burger for now. And then we move on to the next city. Okay, well, all of that stuff we loaded into cache, most of it is useless. So we moved on to the next city here, and we're going to grab the first item again, and it's a disaster. Okay, we load this one in, we swap that one out, load this one in. Okay, go with this one. And now, no, we have to go back to Ann Arbor to get the pizza because we didn't grab it while we were there. Okay? And it's just a complete catastrophe for performance. Okay? So anyway, this is also getting into this idea of you want to really be thinking about what's happening in your cache and how your memory is being loaded and when you're doing it. Okay, can really speed you up. Data layout is a very big deal. So you're going to want to think at least a little bit. It's not that crazy, but you're going to want to think at least a little bit about how am I going to lay out my particles, my particle data. Okay, how am I going to store all that stuff? Your particles are going to have a bunch of properties, and you're going to have to figure out how you want to do it. Okay. So, question. So how do we start working any of this into our games? Okay. Well, this is a very, very common data-oriented approach. Okay. Each row becomes a property of your actor or your object or whatever you're making, your thing. And then each column is an actor. Okay. Now, does this remind you of anything? In fact, just this shape up here should remind you of something. If any of you have taken 484, is Is 485 still called web databases? It used to be called web databases.
It's basically just an SQL database.
Yeah, this is just like a simple tabular SQL database, a relational database. Okay? And that's why they call it data-oriented programming. Okay? So look at this. Relational database. Do a transpose, i.e., take these values and just kind of up there. Okay? Actually, wait a second. No, that's not quite right. Okay. Transpose it, twist it, and this is what you end up with. Okay? Where instead of your actors being the columns, your actors are now the rows. And instead of your properties being the rows, your properties are now columns. And you now have the way that a relational database is typically represented. Okay? And this is basically what you have. Okay? So if you look at our current object-oriented architecture, it just doesn't do this at all. Okay? We tend to have gigantic, Lua components. These Lua components tend to be dispersed all around the heap. And our actors are fairly chunky too, okay? Those tend to be kind of well, actually, no. Our Lua components, our Lua refs, they might be contiguous. It depends where you put them. But what if we could organize and shrink these Lua components, these actors, these objects, all throughout our code base? I think, Jacob, you made an ECS for your follow-up, your sequel to the A2 engine, right?
I did, yes.
Yeah. How long did that take?
Longer than I'd like to admit.
Yeah.
I think about 3 months.
Was it a pain?
I prefer to use the term learning experience.
Yeah. Yeah.
It was a massive thing.
Did the way that you do scripting have to change?
Entirely.
Entirely.
I think it really made me look more at the way that I'm sort of grouping variables and data together.
Yeah.
And really making sure that I'm not just kind of throwing stuff to the wind.
Were you able to keep Lua as a guest language, or did you have to just do C++?
I was,
for
but I'm
scripting?
sure that I was able to keep Lua as a guest language, thankfully. That is the main reason why I'm not entirely sure that it made too much of a difference. But I think that just kind of reorganizing the way that actors and scenes are organized is a really, really, really good thought exercise, and I think it's much more efficient. I just haven't.
Gotcha. Okay. You can imagine loading might be a lot faster.
Oh, absolutely, 100%.
So entity component system is something very adjacent to data-oriented programming. But it is kind of a more flexible architecture than what we chose. We chose a traditional component-based architecture, object-oriented architecture, the likes of what you see in Unity. But ECS is another option. And ECS is a very popular approach, especially on game consoles, which tend to have very limited hardware. Okay, you get improved cache utilization at the cost of some kind of odd and strange code and difficult memory management challenges. You can't tend to set this kind of thing up in languages like Lua or Python because those languages don't give you the kind of control over where your memory is and how it's laid out and how it's loaded that you need, the kind that C++ gives you. Here's the idea behind ECS, and you're not going to implement an ECS this semester, but a few factoid questions could show up on your exam, okay? You want to be careful. An ECS, entity component system, is not the same as what you find in Unity or in our engines. It is different. The terminology sounds very familiar. It's very unfortunate, okay? Because raise your hand if your architecture in your engine has components. Would you say, raise your hand, that your engine architecture has something you might call an entity? Maybe like an actor. They're kind of synonyms. Okay? Raise your hand if you would say that my engine has systems in it. Yeah, we got the actor system, right? We got the Lua system, right? No. Okay. ECS, all of these terms mean something very specific in the world of ECS. And it's really a shame because ECS, every one of those words is very common, show up in just about every engine, okay? But it's not the same. It's very different, okay? Okay, so here's the idea. With an ECS, this is what you end up with. Components are now data only. They don't have any logic inside of them or associated with them anymore, okay? So components are just tiny little containers of data, that's it, okay? No logic, all right? Things like this. You have your position component. You have physics component, which has just some relevant velocity stuff in it. You have a living component, which has HP, hunger, and sleep, okay? That is all you will have now. That's what a component is, okay? No logic, no Lua, business going on, all right? This is a different kind of component than you're used to. This is the opposite of our current approach where our components are kind of chunky, they're written in a slow language, and they house logic, okay? So, small, that's really good for cache, all right? All components sit in typed containers and contiguously, which is very nice, all right? Components, right? You might store all of your components in something like this. You have an array of position components. You have an array of physics components, an array of living components, all contiguous. Maybe it's a vector instead of a raw array, but it's super nice, okay? Now, we talked about components, but what is an entity, right? ECS. What's the E? Well, entities are actors. You know what an entity is? It's literally just an index into these arrays, okay? That's really all it is, okay? So if you want to update actor 0's position or entity 0's position, you need to grab the position component at index 0. You need to grab the physics component at index 0, and then you can alter them, and you've just updated the position of actor 0. It's kind of funky, right? It's kind of ugly. Yes?
So I have a quick, for like Lua, like you mentioned,
yeah.
Is it still okay to use Lua as a guest language in this instance because Lua refs are so small? Or is like the existence of the Lua state and the Lua logic just kind of completely throwing our thing out?
Personally, like if I was building an ECS, I don't think I would involve Lua at all.
No guest language at all, or just no Lua?
I'd probably not do guest language at all. Here's my impression of what happens in a commercial ECS engine. You'll have an underlying kind of layer of logic, even gameplay logic that's written in C++. And then you'll have a very slow layer of Lua logic or some guest language logic that is only meant to kind of tweak the configuration, okay? To kind of change how the underlying C++ systems work. Yeah?
So for every kind of component in this kind of architecture, you need to have num actors, spaces.
Yes. And you're like, that's a horrible waste of memory, right? Well, there are ways to deal with this, right? But you're right, okay? In this kind of approach, if you go with this kind of a naive setup, and maybe it's not naive, it's just a choice. It's a simple choice. The more actors you get, the more properties you have, the more this gigantic database forms. And that database might be sparse, okay? You might not need all that data for everything. So it's a big problem. There are ways to save that and deal with it, but they're kind of a pain in the butt. Yes, real quick.
Yeah, would you say it's possible to make an engine as generic as the class engine using like this kind of pure ECS without a guest language? Or is that more reserved for specific?
The impression I get is we'd have to start moving a lot of serious stuff into C++. But we could probably still keep Lua for tweaking some things and playing stuff, at runtime. But it wouldn't be as flexible, I don't think. I don't know. I'm not sure. I've never built one of these myself. I've never cared to. Okay, so we know what components are. That's the C in ECS. We know what E is, the entities in ECS. But what is system? System is such a generic term, right? Every game has a systems everywhere. Every engine has many different systems, a physics system, an AI system. No, systems mean something very, very particular. A system is a function, a batch of computation that operates on a certain kind of component all at once, okay? And so this is what that looks like. This is a movement system, all right? The movement system utilizes two different types of components, position components and physics components. That's it, to move things. All it does is it iterates through all the actors, and for every position component and physics component, it takes the velocity out of the physics component It applies that velocity to the position component, and there you go. That's it. That's the system. It's nothing more than that. It's just a function that operates on the data, all of the data. Okay? Now, you can get really luxurious, nice ECS systems that are make this much more beautiful, and can be written in such a way that it very easily grabs the right data and not too much of it. And it's a deep rabbit hole. Okay, but this is called every frame, and it iterates contiguously over small objects. One really cool thing in here is that it doesn't have any if or branching logic. It doesn't have to do any checks. The logic is very standardized. It just iterates all over all the components, does its thing, and it has zero branching, which means that it can possibly be accelerated. It can go super fast. So for instance, it's super easy. Everyone in 482 thinks threads are super difficult, and they are. But in this situation, this is called an embarrassingly parallel situation. Why? Because any one index does not care about any other index. Okay? There's no blocking that you need. There's nothing. There's no synchronization that you need. If you've got two threads, simply tell the first thread to deal with the first half of the actors, the first half of the eyes, and stop, and tell the second thread to deal with the second half of the eyes and stop. Okay? And that's all you need. No crazy complex logic or anything. It's very nice. Data-oriented programming, when you do it right, is super easy to parallelize, which is why it's gotten so popular. Our CPU cores are not getting much faster, but our CPUs are getting much more cores. And so data-oriented programming makes use of this change, this trend in hardware. Okay? So keep that in mind. Some find this approach very clear coding-wise. You can get really into data-oriented programming to the point where you say it's easier than object-oriented programming. Okay? But just keep that in mind. Some questions remain. Okay? We have all these components in their arrays. How do you add a new actor? Well, you have to add a new index to every single array. How do you delete an actor? That's a question. Do you perform an erase, and now every piece of memory has to be copied and moved, shifted to the left? Are you going to swap it to the back of the array so you don't have to shift everything as much? Are you going to just leave it there and mark it as null? The assignment spec for homework 9 will tell you what you're supposed to do, okay? Because that's actually a correctness thing when it comes to drawing. So, what if that actor is a middle ID? Well, everything has to shift a ton. It's nasty. It's terrible for performance. What if some actors don't have certain components? What do you do then? Is that even possible in your ECS setup? Okay. Leave them as null or sentinel entries. Isn't that space inefficient? It's going to be very sparse, right? Yeah, you're right. But there are really nice ECS systems out there that kind of have figured out sort of how to deal with these problems with, their own sacrifices that they make. Anyway, Jacob?
Yeah, I was gonna say when I was doing my, I actually don't think that my system is ECS as you described. I think it's just more of a data-oriented version of the current class engine.
Oh, gotcha.
But I think that one of the problems that I ran into that was very annoying to deal with was how do I add an actor into, like, say, the middle of these arrays, or how do I delete one and then not have to reshuffle all of the things and keep track of all the IDs and the indexes because the indexes all change.
Yeah.
So that's definitely something that you need to consider when doing a system like this.
You know what my approach is? Just don't even bother with deleting. It's like, just let it be sparse, and maybe we'll use it in the future. And if you have a new actor that gets created, you can be like, oh, we got this empty slot for you,
so
right in there.
Object pooling?
Yeah, object pooling.
What I did was I did delete them. But to handle like the reshuffling, I had a map of actor IDs to the index that I update. Yeah. And then in order to handle like not deleting a bunch of actors every second, just sorting them again is a pain. Yeah. I just kind of keep the actor dead in there, like I keep its corpse around, and then every like 60 frames or so, I will do a clean sweep.
Nice.
So I don't have to iterate through it all and resort it.
Very good. Defragmentation. Yeah. Very good. All right, everyone, this is your first taste of data-oriented programming. In certain ways, it's very simple. You might have already done it before. In fact, if you learn functions before you learn structs and classes, there's a very good chance you did use it. Okay? Sorry, if you learned arrays before you learned structs and classes, which is a very good chance you did, very good chance you did data-oriented programming, okay? And homework 9 probably requires it if you want to hit your performance needs, but it doesn't need to be crazy, okay? Homework 9 does not ask you to bend over backwards and do 3 somersaults in the air to get this working. It's just a very basic implementation, should take you all the way, okay? And I won't ask for anything crazy about it on the exam either. Yeah, you saw the question we asked last year, and the question was like, did you pay any attention to that one slide that showed you like what this basically is, right?
Probably the one question on the whole exam.
Yeah. Yeah. Oh, really?
Probably,
All you have to remember is big chunky objects bad, small arrays good.
I think it was hard
Okay.
to really internalize what data-oriented was until I actually sat down and redid my entire engine with that. Like, it's kind of an ethereal concept until you actually start doing it.
Yeah, you'll get a feel for it. Don't worry, everyone. Okay, everyone, that's it. Sorry I went a little bit over. You can put your names on the office hours queue if you want office hours help. I'll try and help. One big thing I've noticed is that sometimes it's very difficult for me to help because I don't know your code base. There's some bug gremlin hiding in there, and the best I can do is give you advice for how to debug it. So, keep your expectations kind of low. Okay, we will see you all on Wednesday, everyone. Take care. Yeah.
Two quick questions. So one out of curiosity,
Yeah.
how would you have handled the reshuffling the index thing? You just said you keep them around into object pooling and then just reuse the index later.
Yeah. So on homework 9, this is required that you do it this way. Otherwise, like the image will be rendered slightly differently.
You didn't like the idea of using the map.
Well, I just wanted something very simple.
Yeah, that's fine.
So when a particle, when a particle deactivates,
Oh yeah, for
its
particles that
lifetime
makes
is
a lot
over.
of sense actually.
Yeah.
Because
when lifetime is over, you put it on a queue and basically
Well,
say,
so
hey,
like-
this index is now free.
it's almost a given that you're bringing new ones in all the time. But for the actors stuff,
Oh, for actors?
it's not. For like this is
Yeah,
not
it's
easy for
not
actors. It's not like a guarantee
Yeah.
that instantiation happens often.
Creating
I don't want the
small
memory being.
ones.
Okay, so
Yeah.
that was that. I was curious.
Yeah.
And the second thing was.
Well,
so for
I would prefer wasting memory because most systems just have a shit ton of memory.
That's true.
these
Well,
days.
that's why I only bother actually cleaning it every second or so. But
Gotcha.
so for discussion this
Oh,
Friday.
I've got to end the stream. Take care, everyone. Bye-bye.